Admit it, if not for the title of this video, you would probably think this is an image of the moon's surface. A barren gray landscape dotted with craters. It personally evokes associations with Earth's satellite. And indeed, if Mercury suddenly replaced the moon in the sky, you probably wouldn't notice the difference for a while, at least visually, as both celestial bodies are quite similar in size. However, Mercury is much more massive, 4.5 times more massive than the moon. In fact, it's more massive than Titan, Ganymede, and Pluto combined, as it is the second densest planet in the solar system. It is believed that Mercury harbors a huge metallic core inside, which takes up most of its volume. Such properties are actually difficult to expect from planets if we believe modern models of their formation. In general, until the end of the 20th century, Mercury was one of the least studied worlds in the solar system, and even today, the lack of information about it leaves many key questions unresolved. But that's why we love space, for its mysteries. So in this video, I suggest we dive into the harsh world of the closest planet to the Sun. Despite the difficulties of observation, humanity has known about Mercury for a long time, with the first mentions recorded by the Babylonians as far back as the 2nd millennium BC. They called the planet Nabu. The ancient Greeks, after realizing that the so-called morning and evening stars were actually the same celestial body, named it Hermes. Hermes was the swift-footed messenger of the gods, so the planet's name is likely associated with its speed across the sky. The modern name is the Roman equivalent of Hermes, referring to the fastest god in ancient Roman mythology. Of the 5 wandering stars, as planets were once called, Mercury is the least studied. Unlike Venus, Jupiter, Mars, and Saturn, it is the hardest to observe from Earth. Because Mercury is the innermost planet of the solar system, it always sticks too close to the Sun from our point of view. Thus, although the golden time for astronomical observation is, of course, night, Mercury rises and sets almost simultaneously with the Sun. This means it can only be seen for a short time, just before sunrise or directly before sunset. Moreover, at that time, the planet is observed near the horizon, so most of the turbulent atmosphere blurs the view. Due to its proximity to the Sun, trying to spot Mercury during the day can be quite dangerous for both telescope optics and the person looking through it. Large telescopes are often not allowed to observe Mercury due to possible damage. Even the legendary Hubble Space Telescope, which can see galaxies in the early universe, has never directed its gaze toward Mercury for fear of damaging its sensitive optics. For the infrared James Webb Telescope, it would be outright suicide. It's no surprise that before fully fledged robotic missions to the planet, little was known about Mercury. So, this is the smallest planet in the solar system, which suffers the most from solar radiation. At its closest point to the Sun, from Mercury's surface, our star would appear 3 times larger than from Earth and 7 times brighter. Mercury's orbit is tilted 7 degrees relative to the plane of the ecliptic, the most of all planets in the system. Nevertheless, it sometimes passes directly between Earth and the Sun, much to the delight of astronomers who are not afraid to look at the solar disk, of course, with the help of proper equipment. Mercury transits occur roughly every 7 years, with the last one observed in 2019. The small black dot against the backdrop of the giant solar disk serves as a reminder of the immense size of our star. In fact, Mercury's orbit is something special, and imagining it is not so simple, but we will try to visualize it at least partially. In addition to being somewhat inclined relative to the plane of the ecliptic, it is also the most eccentric orbit of all the planets in the system, meaning its shape is somewhat elliptical. Traveling around the Sun in 88 Earth days, this egg-shaped orbit causes Mercury to come as close as 47 million kilometers and as far as 70 million kilometers from the star. But while it moves faster than any planet, Mercury rotates relatively slowly on its axis. One rotation takes 59 Earth days. This means that for every 2 full orbits around the Sun, Mercury rotates 3 times on its axis. But I emphasize relative to the stars. This doesn't mean that during 2 Mercurian years, the Sun rises and sets 3 times. Actually, it only does so once. Here on Earth, we are used to thinking that the movement of the Sun across the sky is caused by the planet's rotation on its axis, which is true, but not entirely. In fact, the sun's movement is also influenced by the planet's motion around the sun. We don't particularly notice this because our planet rotates relatively quickly on its axis. But Mercury is different. For an observer on its surface, the sun would move from east to west just like on Earth, but it would do so much more slowly. Due to Mercury's slow rotation on its axis, its movement around the sun greatly affects the sun's apparent motion across the sky. This actually leads to an effect where a single solar day lasts twice as long as a Mercurian year. So, for the sun to fully illuminate Mercury's surface, it takes 2 local years, or 176 Earth days. It gets even more interesting when the planet is at its closest point to the sun, called perihelion. Once again, remember that the sun moves across Mercury's sky just as it does on Earth, from east to west. But at perihelion, it will appear to an observer on the surface that something is wrong with the sun. Its usual motion suddenly seems to break. It seems that at some point, the sun simply stops, then even begins to move backward, to the east. And only after this strange maneuver does it resume its normal westward motion. This is explained by the fact that as the planet approaches perihelion, its orbital speed increases, and at a certain moment, it matches the speed of the planet's rotation on its axis. At this time, for an observer on Mercury, the sun stops moving across the sky. The closer the planet gets to perihelion, the faster it moves. So at some point, its speed will exceed the rotation speed, causing the sun to drift backward. Finally, after crossing perihelion, the normal westward motion of the sun resumes, as the rotation speed once again exceeds the orbital speed. During this solar dance on Mercury's equator, there are places where the sun lingers in the sky for 2 to 3 Earth weeks. Considering that Mercury is in perihelion, the surface of the planet during this period can heat up to temperatures of 430 degrees Celsius. However, due to the lack of a typical atmosphere, the heat does not transfer to the night side. So during the long, cold nights, the temperature can drop to minus 180 degrees Celsius. Such a large temperature difference cannot be found on any other terrestrial planet. Nevertheless, it's still not as hot as Venus, where radiation can hardly escape, continually heating the planet. But Mercury's temperature difference could be even greater if the planet were tidally locked to the sun. By the way, astronomers actually thought this was the case until the 1960s. They truly believed that one side of the planet was always facing the sun. But thanks to the Arecibo Observatory, they managed to confirm the existence of Mercury's rotation. Since Mercury completes several orbits around the sun while Earth only completes one, about 3 to 4 times a year, Mercury overtakes Earth. This creates an interesting optical illusion where the planet appears to move backward across the sky for about 3 weeks. Astronomers call this motion retrograde. The effect is quite intriguing, but don't believe those who claim that this somehow affects your life. In fact, studying Mercury is difficult not only with telescopes. Sending a probe to the planet is also not an easy task. According to the European Space Agency, it's actually easier to send a mission to Pluto as it requires less energy. The reason again lies in Mercury's proximity to the Sun, as it is located deep within the star's gravitational field. If a space probe aims not just to fly past the planet while orbiting the Sun, but to actually enter orbit around Mercury, the spacecraft must constantly brake against the immense gravity of our star. Thus, it either needs to be equipped with a huge amount of fuel to decelerate with its engines, or slow down using the gravitational pull of other planets, including Earth, Venus, and Mercury itself. In fact, spacecraft can not only speed up using planets, but also slow down and change their trajectory if needed. Several such flybys are necessary to decelerate sufficiently before entering orbit around Mercury, which is why the journey to the planet takes quite a long time. It's no surprise then that only 3 space probes have closely studied the surface of the planet closest to the Sun. The first was Mariner 10, which flew past Mercury in the 1970s while orbiting the Sun. Mariner flew by the planet 3 times and managed to photograph about 45% of its surface, as well as make the first detection of its mysterious magnetic field. After a 30-year gap, NASA launched a dedicated mission to Mercury called Messenger, which aimed to become the first probe to enter orbit around the planet. By the way, the name is just an acronym and has nothing to do with any messages. After its launch in 2004, the probe followed a complex path, using the gravitational assistance of Venus and Mercury over several years. Finally, in 2011, after a 7-year journey, it entered orbit around Mercury, and its 4-year mission provided us with most of the information we have today about the planet's surface and internal composition. So, the surface indeed resembles the surface of the Moon, as it is covered with impact craters caused by collisions with meteoroids and comets. The largest impact basin, known as Caloris Planitia, has a diameter of over 1,500 kilometers. It was formed by a collision with a massive asteroid early in the planet's formation. This is one of the largest craters in the solar system and, at the same time, the most significant feature of Mercury's surface. The impact was so powerful that it triggered lava eruptions. Interestingly, on the opposite side of the planet, directly across from Caloris Planitia, there is a large region of hills and depressions known as the Weird Terrain. In 1975, during one of the studies, scientists hypothesized that the weird terrain might be the result of shockwaves generated by the asteroid impact. Moving across the planet's surface, they met on the opposite side, and the high stresses in the crust could have caused deformations in that specific location. Also, within Caloris Planitia lies a smaller crater called Apollodorus, which astronomers often refer to as the Spider, due to the many troughs radiating from it. However, upon closer inspection of the crater, it becomes evident that it is not actually located at the center of the fractures, so it may not be related to them and could have appeared later. So, what caused these depressions? Well, this is one of Mercury's mysteries that remains unsolved for now. Another interesting crater, named after Rembrandt, is the second largest after Caloris Planitia. Its diameter is estimated to be 715 kilometers. It appears to be one of the youngest large impact craters on Mercury's surface and was likely formed during the late heavy bombardment period nearly 4 billion years ago. It is intriguing due to its unique system of concentric and radial ridges and troughs, which resemble the pattern of a wheel with spokes. There is nothing like it on any other moon or planet in the system. It's worth noting that craters on Mercury are named after famous writers, poets, and musicians from around the world. Although most of Mercury's surface appears grayish-brown, traces of past impacts add some diversity to the overall picture. In particular, there are bright streaks near the impact sites, known as crater rays. The immense amount of energy released during an impact not only creates a deep pit, but also pulverizes large quantities of rock. Some of this pulverized material is ejected far beyond the crater and falls on the surface in the form of lighter-colored rays. These rays are brighter because the smaller rock particles reflect sunlight better than larger pieces. However, over time, the rays darken due to the effects of solar wind and dust deposition. Similar bright rays can be seen on the Moon, and their spread is even greater than on Mercury's surface. This is because the more massive Mercury has stronger gravity, preventing the debris from dispersing as far. One of the unexpected features of the surface of the planet closest to the Sun is the presence of water ice. Although it's hard to imagine given the planet's location, it is still possible at its poles. The fact is that Mercury has a very small axial tilt of just 0.034 degrees, so there are no seasonal changes like those on Earth. But this also means that the planet's poles are not illuminated at a direct angle, and therefore a considerable amount of ice can be found inside craters and in permanently shadowed areas. The first traces of ice were discovered using radar observations by the Arecibo Observatory based on measurements of the planet's surface reflectivity. Later, Messenger reliably confirmed this discovery, with its data indicating the presence of ice in 3 large craters at the planet's north pole. To this day, scientists are unsure how the water got there, whether it is the result of comet impacts or if water vapor was directly released from Mercury's interior. Or perhaps hydrogen ions carried by the solar wind could have interacted with oxygen on the planet's surface, forming water. Nevertheless, even the presence of water on the surface is not as intriguing as the existence of such structures. Long, winding cliffs, several hundred kilometers in length and up to 3 kilometers in height. They are interesting not for their appearance, but rather for their origin. Despite the fact that Mercury is smaller than some moons, such as Titan and Ganymede, the planet's diameter seems to continue decreasing. As Mercury's massive core cools, it solidifies, thereby reducing the planet's volume and consequently, its size. Naturally, this process has its reflection on the surface. The crust contracts, forming wrinkled ridges and faults. These arise because, under the force of gravity, the planet's crust is forced to adapt to the shrinking interior, causing it to fracture along inclined planes and be pushed upwards. This is Mercury's own version of Earth's thrusts, extensional faults, and strike slips that occur with the planet's crust. One of these cliffs, called Discovery, is 550 kilometers long and up to 1.5 kilometers high. Note how the walls and floor of two impact craters were deformed by thrusting. This indicates that the deformation occurred after the craters formed. The Messenger mission also found small faults that are less than 50 million years old, suggesting that Mercury, like Earth, is still a tectonically active planet. It continues to cool and contract, meaning that new faults will keep forming. As a result of this process, the planet has likely already shrunk by about 7 kilometers. This, in turn, means that Mercury still experiences earthquakes, or rather, Mercury quakes, since the faults must be accompanied by seismic activity. Seismometers installed on the Moon by the Apollo missions detected tremors up to 5 on the Richter scale, but considering the size of the faults on Mercury, its quakes must be much stronger. Thus, it turns out that Mercury is still warm enough to continue contracting. The presence of a magnetic field, first detected by Mariner 10, also suggests that there are still hot layers beneath the planet's surface. Theoretically, magnetic fields are generated by the relatively fast rotation of a planet and a molten core inside it. But tiny Mercury takes 59 Earth days to complete one rotation, and it's so small that its core should have cooled long ago. Nevertheless, Mariner data showed a magnetosphere similar to Earth's, aligned along Mercury's axis of rotation. Astronomers hypothesized that such a magnetic field could only be a remnant of past core activity, left imprinted in the magnetized rock. However, Messenger confirmed that this field is dipolar, meaning it has north and south poles and must be generated in the same way as Earth's, and the planet's crust seems to show no signs of remnant magnetism. So, Mercury's iron core must still consist of both solid and liquid layers, which, through their rotation, generate the magnetic field. All this internal heat may be released due to tidal heating of Mercury, whose eccentric orbit causes it to periodically move closer to and farther from our star. As for the atmosphere, the planet almost doesn't have one. Almost because Mariner data indicated the presence of only a thin exosphere. An exosphere is when the density of molecules is so low that they virtually do not collide with each other. For comparison, Earth's exosphere begins at an altitude of over 500 kilometers above the surface, higher than the orbit of the International Space Station and roughly equal to the orbit of the Hubble telescope. On the other hand, Mercury's exosphere begins right at the surface and contains various chemical elements, including hydrogen and helium. These two elements likely come from the solar wind and linger near the surface only briefly, perhaps a few hours, before continuing their journey away from the sun. Atoms of other chemical elements, such as oxygen, sodium, potassium, and calcium, likely originate from the planet's soil, ejected as a result of meteoroid impacts or bombardment by particles from the solar wind. Interestingly, when the solar wind hits the exosphere, it pulls away some of its atoms, creating a long, striking tail, much like a comet. Due to the fact that sodium atoms scatter yellow light very well, with certain filters, this enormous tail can be seen, even though it is almost invisible to the naked eye. Mercury's core is its greatest mystery. It is enormous, 4,000 kilometers in diameter, or about 85% of the planet's total diameter. This poses a serious challenge to planetary formation models, as it is difficult to accumulate such a large core without proportionally increasing the size of the planet. Conclusions about the internal composition of the innermost planet were drawn from numerous measurements using various methods. During its close flybys of Mercury, Messenger recorded tiny variations in the planet's gravitational field. This allowed scientists to understand how the density of matter is distributed inside the planet. Through ground-based radar observations, astronomers studied Mercury's rotation in great detail, looking for so-called librations, slow oscillations of the planet as it orbits the Sun. These showed that the planet's mantle is not rigidly attached to its core. Combining this data with the presence of a magnetic field, astronomers have developed modern models of Mercury's internal structure. It appears that the innermost planet has a solid crust and mantle made predominantly of silicate rocks, just like Earth. The mantle covers the planet's outer solid core of iron sulfide, beneath which lies a layer of liquid core, and even deeper, the planet's inner solid core. Thus, with most of its composition being iron, Mercury is the second densest planet in the solar system, after Earth. How tiny Mercury managed to accumulate such a massive core is one of the greatest mysteries of the solar system, and scientists have been puzzling over this question for decades. So far, the most amusing hypothesis, as is often the case, involves a giant collision. At some point in the past, ancient Mercury may have experienced a global catastrophe similar to the collision between Earth and the hypothetical planet Theia. Afterward, the planet's outer rocky layers could have been lost, leaving behind a metal-rich planetary core. This, by the way, would also explain why Mercury's orbit is so elongated. However, the idea of a collision was dismissed after the MESSENGER mission, which found high concentrations of elements like potassium and sulfur on the surface. If a collision had indeed occurred, the extreme temperatures would have simply stripped the planet of these volatile substances. A softer explanation is that the Sun's magnetic field might have played a role. In the early days of the solar system's formation, iron particles could have been drawn in through the dust and gas by the Sun's magnetic field. Therefore, planets that formed closer to the Sun would have accumulated more iron. This is why, according to a 2021 study, Mercury, Venus, Earth, and Mars have different proportions of metal and rock. Mercury's iron core makes up nearly 2/3 of its mass. Earth's and Venus's cores make up about 1/3 of their mass, while Mars's core accounts for less than 1/4 of its mass. Thus, researchers believe that the density and percentage of iron strongly correlate with the strength of our star's magnetic field. However, to confirm this idea, at least one more planetary system similar to the solar system needs to be studied. In fact, there are many hypotheses, but none so far offers a definitive explanation for the strange internal composition of the first planet. Therefore, it's clear that Mercury needs more thorough investigation. The only current mission to the Iron Planet is called Bepi-Colombo. It's a joint project of the European and Japanese space agencies, which launched in 2018 and is set to reach Mercury in 2025. The mission consists of 2 spacecraft, which, after a long journey to the planet, will separate and orbit it, providing us with more new information. The European spacecraft will focus on studying Mercury's surface, while the Japanese spacecraft will investigate the planet's magnetosphere. In 2021, Bepi-Colombo performed its first gravity assist flyby of Mercury and took its first images of the surface. Thus, it became the 3rd spacecraft to achieve this. Once in orbit around the planet, the mission is expected to last about a year, with the possibility of extension for another year. Keep in mind the harsh conditions in which the equipment must operate, so the relatively short mission duration should not be surprising. For reference, MESSENGER was also designed to operate for 1 year, but it worked for 4. In any case, if everything goes according to plan, Bepi-Colombo may be the mission that finally uncovers the mystery of Mercury's core and its other peculiarities. As a result, Mercury may lose its reputation as the most mysterious planet in the system.